Hello everyone, my name is Ira J. Panuncio and I'm here today to talk to you about semiconductor. So what is semiconductor? A semiconductor is a material that has electrical conductivity between that of a conductor and an insulator. Semiconductors are an essential component of modern electronics and they are used to create electronic devices such as transistors, diodes, and integrated circuits. Semiconductors are typically made of silicon, although other materials such as germanium, gallium arsenide, and silicon carbide can also be used. When a small amount of impurities or dopants are added to semiconductor, it can become either a p-type or n-type semiconductor, which allows it to perform specific electrical functions. Now, let's see the theory of semiconductors. The theory of semiconductors is based on the behavior of electrons in the material. Semiconductors are made of atoms with a small number of electrons in the outermost energy level or valence band that are easily excited to a higher energy level, conduction band, by thermal energy or by an external electric field. This results in an increase in electrical conductivity. In pure semiconductors such as silicon or germanium, the valence band is completely filled with electrons, and the conduction band is completely empty at absolute zero temperature. However, at higher temperatures or with the addition of dopants or atoms of different elements, some electrons in the valence band can be excited to the conduction band, creating free electrons and positively charged holes in the valence band. The number of free electrons and holes in the semiconductor depends on the temperature and the amount and type of dopants added. This creates different electrical properties in the material, allowing it to be used for specific applications in electronic devices. The behavior of electrons in semiconductors is described by quantum mechanics, and the theory of semiconductors involves complex mathematical models and calculations to predict the electrical properties of the material. Now let's talk about principles of semiconductors. The principles of semiconductors are based on the behavior of electrons in the material, which are influenced by quantum mechanics. The following are some of the key principles of semiconductors. Number 1, the band structure. It is the energy levels of electrons in a semiconductor are divided into two bands, the valence band and the conduction band. The energy gap between these bands determines the conductivity of the material. In insulators, this gap is large, while in conductors, there is no energy gap. Next is doping. The addition of impurities to a semiconductor can alter its electrical properties. Dopants are atoms of other elements that have either more or fewer valence electrons than the semiconductor material, creating either excess electrons, n-type doping, or holes, p-type doping in the material. Carrier mobility. The movement of electrons and holes in the semiconductor is influenced by the mobility of these carriers, which is determined by factors such as temperature, doping. Combining of two different types of semiconductors creates a junction which has unique electrical properties. In a p-n junction, for example, the p-type semiconductor has an excess of holes while the n-type semiconductor has an excess of electrons. At the junction, these carriers diffuse or recombine, creating depletion or region with no free carriers. Lastly, Schottky barrier. When a metal is in contact with a semiconductor, a barrier is created that prevents the flow of current. This is known as the Schottky barrier, and it is caused by the difference in work functions between the metal and the semiconductor. Understanding these principles is essential for designing and optimizing electronic devices such as transistor, diodes, and integrated circuits. Now, let me introduce to you Vanessa Mural to explain the types and classifications of semiconductors.
Types of semiconductors. Semiconductors can be classified as intrinsic semiconductor and extrinsic semiconductor. An intrinsic type of semiconductor material is made to be very pure chemically. It is made up of only a single type of element. The most common intrinsic semiconductor elements are germanium and silicon. They have 4 electrons in their valence shell, which is called tetravalent. Extrinsic semiconductor. The conductivity of semiconductors can be greatly improved by introducing a small number of suitable replacement atoms known as impurities. Doping is the process of adding impurity atoms to a pure semiconductor. Extrinsic semiconductors are further subdivided into n-type and p-type semiconductor. The p-type semiconductors is defined as intrinsic semiconductor that has trivalent impurity atoms such as indium and gallium added it to make it a p-type semiconductors. The majority charge carriers in these semiconductors are holes, while the minority charge carriers are electrons. The density of holes is greater than the density of electrons. The accept level is primarily located near the valence band. The N-type semiconductor is defined as intrinsic semiconductor that has pentavalent impurity atoms such as Sb, as added to it to make it an N-type semiconductor. The majority charge carriers in this semiconductor are electrons, while the minority charge carriers are holes. The density of electrons is greater than the density of holes. The donor level is primarily located near the conduction band.
And now I'm discussing the semiconductor circuit schedule. We have the P type, this is the P type, the positive charge, and the N type, negative charge. This part is the P junction, and the P type and the N type combine. The electron of the N type, the P type, the P type, and the N type. The electron is available in P region, and the pulse is available in N region. In this space region, the movement gives the rise to the diffusion current, and also we have forward bias. The forward bias is the external voltage is applied approximately in the ion. This voltage cancels the potential barrier and provides the low resistance to the flow of the current. The forward bias means that the positive region is connected to the P type of the supply, and the negative region is connected to the N type of the negative supply. And the reverse bias is the negative region is connected to the positive terminal of the battery, and the positive region is connected to the negative terminal of the battery. The reverse potential is the strength of the potential barrier. The potential barrier resists the flow of charge carriers across the junction. If the reverse bias creates a high resistive path in which the current can flow, no current flow through the circuit. This is the structure of the NPs. In this device stage, the premium at 1 degree Celsius, the diffusion region of the PN junction is made of this space. This PN junction has a 4-carbon voltage, which is the bottom. Germanium is 0.3 volts, silicon has 0.7 volts, gallium arsenide has 1 volts. This PN device or a diode has a terminal, positive terminal which is ion, and the white end is a negative terminal which is the cathode. And we proceed to application of a semiconductor, which is used to almost every sector of electronic. First is the consumer electronic. This is a phone, laptop, tablets, microwave, brain, with the use of semiconductor component such as IC, diode, or transistor. And next one is the embedded system. Are all computers from the part of the large machine that can control the device and allow user for interactions. Next is the terminal. Terminal conductivity can be used as a cooling agent to contain the thermoelectric application. Next is the LED. This is available in liquid or from a clean oven film and produce light and use LED. Next is the solar. Solar cell is the production of a solar cell for the power solar panel or photovoltaic. That's in the presentation.